Okay, so have your test back. What I'm going to do is what I normally don't do, but it's connected with the next thing I'm going to say. So we're supposed to have 3 tests for this week. Because of the mix-up I had with the Vancouver meeting, there's no way I can write it. There's no way I can have another test written by next week. And it's toward the end of the semester. So I'm going to do what I normally do not do. Okay, so this is all conspiring. I'm going to let you do corrections in lieu of that on the 3rd test on this exam. There's a little catch here. You have to come by and you have to chat with it, okay? Because I want you to do really well on it, because I want you to understand the material. I mean, I was actually happy with it. But there's some things that people I would actually try to be more organized in your work, just in a general thing. I think if people were a little more organized in how they did things, a lot of the kind of boneheaded things that people did, and I'm pretty certain you know, probably would not have happened. Try to be a little more organized in your work. And I think you're going to find it's actually going to work well, better. But I want you don't, okay, if you're happy with your grade, and you don't have to do this little exercise of corrections. Okay. However, in lieu of not having a test next week, this will be kind of our this will make the 3rd test. What I'll do with the corrections, I honestly have no idea. I don't think I've ever done the same thing twice. And anytime whenever I have a lot of corrections, I don't think I've ever done the same thing. I will need them fairly soon, probably by Thursday or Friday, because most likely they're coming with me to Vancouver. And I will be spending my evenings in Vancouver going through an enormous pile of grading. Okay, I'm gonna have some fun. Okay, there will be some amount of grading after you. Yes.
So are we gonna have a 3rd one?
What did I just say?
I didn't.
Okay. See, Paco. Okay.
So is there a final still?
There, of course. James made it funny. Okay, there is a final, and it'll be during finals week, and there will be some proctor that is not here. Okay, and then what it'll be is to encourage you to really master this material on the final exam. And I only give comprehensive final exams because it's a final exam. They should only be comprehensive. However, to encourage you to look over this stuff and really master it, I will take questions from that exam and either put them directly on there or with slight modification on the exam. So at least you'll know some of the exam questions. Yes.
So are we going to have a 3rd then?
I think it's quite clear that the answer is no, that the corrections are going to be in lieu of that.
Oh, so the correction is going to be a 3rd then?
I think that's what I've been saying. Yes.
Wait, but what is the correction? Are we just going to take our test and just...
And you correct it. Gee, what could the corrections be then?
And then you're all correct.
I've got a perfect score on the 1st.
Okay. If only it was clear what it means to correct it. You know, it's so unclear. Okay. So yes. But the stipulation is I want to come back because I want to go over it with you to make certain that you really understand what we're going on. Okay.
Where does that meeting with you come in? Like,
It's called my office.
no, I mean, like, should we do that before we do the corrections or after?
Well, I would do it as soon as possible, just because I'm under the enormity of the grading that I'm behind in is really starting to, sink in. I'm actually there's a certain level of panic coming on me, so heavy breathing, and getting ready to pass out because of the amount of work I have to do. Yes.
So do we just need to do the exercise we didn't get the point on?
Yeah, if you haven't correct, there's no reason to correct it.
Yeah, okay. I was going to do the whole thing. Again.
I would not grade the whole thing. I will look to see what is not correct, and I'll look at that. Now, as an exercise, get ready for the final. I may not get anything to do. Okay. Questions? Yep.
What day is the final? No.
I'd have to check. So it's going to be whatever's on the. So it's ever on the syllabus. 10, 12. Saturday. 10 to 12. I will be coming back that day, but I have no idea what that means. I think Colin said it was returning on Saturday. I don't know if that really means that arriving late at night, early in the morning. I honestly have no idea. If I'm here, then I will proctor the exam. If not, it'll be somebody else.
You have the facility proctor too.
That's the possibility. So that's but Vasily might be a busy boy that. Questions? Okay. So I'll say more about the final next week, and I'll come up with a study sheet while the other chapters. I'm going to leave the hydrogen atom about a day or two before I really want to. I'd like to say a little bit more about it. But I want to also make certain I get to a certain amount of special relativity. So I want to finish up kind of the last topic before we go to special relativity, which is going to be basically quantum statistics, and in particular black body radiation. Quantum statistics. And black body radiation. Next spring is I will be teaching statistical mechanics for the last time in probably about the upper level physics courses. Dr. Kirtland and I we alternate back and forth. So he'll have a course for 3 years, I have a course for 3 years, and then we alternate. So next semester will be next spring will be the last semester I do statistical mechanics. The entire course is basically quantum statistics, not entirely, but that's a large fraction of it. I would actually recommend anyone who's still here who hasn't graduated to take that class, even the engineers. You will find that class utterly amazing what it will do for your background, which you can do a stat. It's really, it's the microscopic reason why thermodynamics works. It's actually very important. So I'm going to state 2 things as a fact. And no matter what, even if I had a little more time, I would still have to do that because we just don't have the ability to develop the entire thing. To drive these equations in all of its story detail, depending on which one the story detail is about a month. And I don't, because there's a lot of background that I have to get to that. So I'm just going to have to sadly just hit the result. So what is quantum statistics? And is that showing up? I'm thinking it is. Okay, so what are quantum statistics? So let's say here's an energy level diagram. And here's some energy levels. This is D1, D2, D3, D4, so on and so forth. Doesn't matter what it is. Okay. I could have some generic level here, EI. This is the energy level. I might want to know how many particles, what's the average number of particles in that state? So I could ask, what is the average number of particles and the energy level? And that's really going to depend on whether I have what type of particles. Yeah, whether my particle is a fermion or whether my particle is a boson. Okay, so the answer to this is this depends. This depends on whether the particle is a fermion or a boson.
You ever do a mixed systems where you have both?
You can, but that's not what you do is that the fermions obey the what are called fermi-directed statistics, and the bosons obey what are called boson statistics. So they just factor. So what happens here? Let's start with fermions. Okay, so the average number of fermions of, let's say, identical fermions in energy level EI is given by the Fermi-Dirac distribution.
When we say identical, we mean identical energy, right? Not identical.
No, I mean, identical electron, you have all electrons or all protons or all neutrons. It's all the same level of fermion. Okay. So it's going to be given by something called the Fermi direct distribution. Okay, Dominic has seen actually the golden proof of these things here. And he will be the first to testify that we did not start off with that. To build up all the technology for it took some time. And so there's no way I can do an adequate job with it. So sadly, I just have to stay with this. But again, when you take that course, and actually everyone in this room should, I will go into that in extreme detail. In fact, I'll give you two different derivations. Okay, so we're going to call this FD for Fermi Dirac. This is an energy EI. Yeah. And I'm eventually going to drop that subscript I just a little bit. It's going to be given by 1 over e to the EI minus EF. Hey, what do you think EF is? That's your Fermi energy. That's also called the chemical potential. So sometimes you'll see a mu there, but don't worry about that. Okay. Over kBT. Okay, plus 1. Now let's talk about kB. Okay, kB is the Boltzmann constant. And anyone know how you define it formally? It's actually the ratio of two other constants. R, what is R? Yes. The ideal gas constant. Okay, divided by Avogadro's number. So it'd be this 8.314 divided by 6.02 times 10 to the minus 20, 10 to the 23rd. To work this out, kB is 1.38 times 10 to the minus 23rd joules per Kelvin. And this T here has to be measured in Kelvin. T is measured in Kelvin. Okay. So what I want to do is graph this, see what it looks like. It's going to make, even though you're not going to know where the equation comes from, the shape of it is going to make perfect sense. You're going to look at it and go, oh yeah, I may have guessed that. So let's actually figure it out. Since I walk back and forth, always look.
Should get a little like thing on your belt that holds it.
I should. Or for an oven, just, I really want nested blankets. Just looked it up. There's another blanket nested up. And there's another blanket. So again, when you guys become multi-billionaires, you don't know what to do with several billion. Building dedicated to me with my room with nested blackboards. Okay. I also want the entire building to go up, just raise up on like a hydraulic lift and rotate, and then go back down. It serves no function, but I really want to be in a building that goes up, rotates, goes back down.
I can do that in a really small building.
And if I'm really small, I would take you up on the offer. Well, it turns out that I would like something that, I and my colleagues say we're doing. So let's make a graph of this. So let's graph the Fermi Dirac distribution versus E at T. So let's go through this. Okay. So this T here is going to be really, really tiny. What do you know if you divide something by something really, really tiny? Very, very big. It's very, very large. Okay, so the question is what's going to happen. So let's say my EI is greater than EF. Oh, actually, let's go the other way. Let's say the EI down here. This is E. That's the
You approaching zero instead of at 0.
Well, I'm going to say at 0, but in order to do the argument, I'm going to say it's approaching 0. So I'm saying this T is really, really small. Now, what happens if this EI value here is small compared to EF? What's the top? Is negative. So if you take something negative divided by something really, really tiny, what does that become?
Very large.
a very large negative vector. What is e to the minus negative large? It's going to go to 0. That makes sense? So this goes to 0. And so what does that become? 1. So what I'm going to have here is I'm going to have 1 here. Why does that make perfect sense? Remember when we had these infinite wells and we were putting in particles, what did we say? What was the Fermi energy, first of all, at T equals 0 in those cases? As your maximum energy, that was your Fermi energy. We started putting particles in here, and the ground state, or in, let's say the first energy level, how many particles could go there? If we had spin a half, could have 2, spin up and then spin down. So why is this saying 1 here? Well, what it means here is that to get the actual, if you put in like spin a half particles, I'd have to multiply this value by 2 because I could have 2 particles. The point is that this is not 3 or 4 or 12.8. This can only be 1. Why? Because if I can, let's say I have like this, let's say I'm only dealing with spin up particles, I can only put 1 spin up particle in that energy level. That has a maximum occupancy of 1. Now, what happens when I go over here? This E is greater than EF. Now let's go through this argument. So if I have E minus EF, and E is greater than EF, what's the numerator? Positive. T is really, really small. So what can I say about this whole exponent? Large. Very large. What is E to the really, really large? Really, really large. What is 1 divided by really, really large? 0. So what's going to happen here, that this you get something like this. Okay. And we've seen that before. That's not too surprising. That's at T equals 0. Now, if I start increasing the temperature, what's going to happen? Start increasing the temperature, what can some of those particles do? They can actually go to excited states. Now, which ones are going to go to the excited states?
Ones that are.
I mean, is this one over here going to go to an excited state over here? No, it's actually going to be the ones really, really close to the Fermi energy. They're going to have enough energy to be excited here. These can't move here because they're going to be blocked by the Pauling exclusion. So only those ones actually close to EF can actually move. So these actually came over here. So what's going to happen is that this is at T equals 0. What's going to happen is that this graph is going to come down here like this. That's going to happen. Go like this. So this is going to be at T, not equal to 0. These particles here actually go into the excited state. So these would be electrons here in some excited state. And as I keep on increasing this temperature, this is going to start going more and more. Okay. Questions from that? Okay, I'm going to give you then what happens if our particles are then bosons. What happens? And again, if you take the statistical mechanics course, I will drive this in extreme detail. It's actually it's a beautiful derivation. And it's actually not hard as long as you have the technology. If you have the technology, to be honest, this derivation, once you get the technology, this derivation will take almost no work. You calculate one little thing, you take a little derivative with respect to some variable, Shazam, you get this immediately. There's no work. And you can tell, well,
You gotta tinker with it a little bit to get that form. It has not to be your form first.
sure, okay, but you don't have to do a lot, but it was easy. Okay, but you do have to get to a certain. So, see, commercial for the plants. Actually, again, if you're an engineer, the physicists and the astro people should be in there. Should very well. Physics, you have to. Astro, you're going to ship because you use this stuff all the time. Engineers, when you use any type of materials, ceramics or glass, you use this all the time as well. You really. Okay, so let's talk about this. What happens if the particles are bosons? Okay, what do bosons not do? They do not obey their Pauling exclusion rules. So what's gonna happen here, this isn't gonna flatten off like this in one. This is gonna actually be as high up here as you want this to be. So what happens is you get the exact same form here with one little difference. It turns out you get a minus sign here. And then this EF, you don't have a Fermi energy because it's basically a boson system. You get this thing called mu, and this mu is called the chemical potential. Very frequently, that chemical potential is zero. I'll mention just to prove this. So in this case, the answer is you get the Bose Einstein. That's given by. It looks just like that with just two lower chains. So you get this EI minus mu over KBT. So it looks just like that, except the EF gets another name. You can actually call this EF, this is a chemical potential. So I could call this minus one. Okay. So this mu here is the chemical potential. And it's basically the energy you have, it takes to add one more particle to the system. Very frequently, the mu is going to be zero. So the mu is the energy it takes to add one more particle. Often for bosons. Mu. No, we need those windows open because it's 4,000 degrees in here. So that noise is absolutely driving me nuts. Okay, it's just.
Go for Roxanne.
Have to think. Getting late enough in the semester, not thinking clearly enough, I have to stop for one thing. That's wrong.
We're practicing our arts in discovering potential.
So I'm not going to worry about what happens when t equals 0 because it turns out I have to do something more fussy. So I don't want to deal with the t equals 0 case. I'm just going to show you generically what this is. So for non 0 t, or t not equal to 0, and this is the case we did it for a black body radiation. Okay, what happens here is that basically it's like that. You can have as many particles as you want down in the ground state because there's no limit on it. Okay. There's a couple little things I'm sliding under the table here that I don't want to talk about, but we will. This is for mechanics class because we'll work out the superfluid piece, stuff like this. It's actually quite a beautiful little tiny calculation. Not that tiny actually calculation. It looks like this. Okay. Now what happens here is that this tail part here and this tail part here actually end up looking the same. If you're for high enough temperatures, it turns out that this part here and this part here, they end up becoming the same. Okay. So what I want to do is an application of this, and it's probably one of the most famous. Well, there's a lot of famous applications. The one we're going to do in this class is how every modern physics course starts. Is after you start off with spectral relativity, the first thing you talk about is black body radiation. It's asked for quantum mechanics starting. I did not start there because basically we didn't have the technology to understand it well. Now with this, what we've done now, I can actually show you exactly what those equations. why we're doing things in kind of a first order. Okay, so let's use both sides. Let's use both sides and to calculate black body radiation. So who's the first one to do this? Okay. It's actually a plane, okay, or Planck, I guess it's a German pronunciation. And this is actually the origin of quantum mechanics. So this is done first by a Max Planck. In 1900, and he solved the problem by assuming that that light, wait, sure, particle, both, okay, has an energy of HF. Okay, he said that the energy of light, photons, proportional to the frequency, so that started off E equals HF. That was the very origin of quantum mechanics. So he solved this problem. By assuming the energy photons was directly proportional to F. We know this better as E equals HF. Unless we're a little tricky, I mean, we're not going to use it in that form in lab in our derivation because we've never seen this form. We're going to multiply everything 2 by 2 pi. What do you know about H over 2 pi?
H bar.
It's H bar. Then 2 pi F. I agree. Which is angular frequency omega. So this is the form we're going to do things. So the question is, what is black body radiation? So you're both in cosmology? Who's doing cosmology?
I don't think that's the class taking engineering science.
Okay. I mean, next month in the fall.
Oh, yeah.
Are you in cosmology? Okay. Well, if you're going to be dealing with, you're going to see black body radiation, basically the derivation there. Statistical mechanics, you're going to see the derivation. You're going to see this derivation, especially begin astrophysics, a whole lot. So this will be your first detailed incursion into this. No, it will not be your last. Okay, so what is that? Well, we're going to take basically, this is a hollow metal cavity. And we heat it to some temperature. Turns out the international symbol for heat is a little candle. And that's the international symbol for heat. Okay. And this is gonna be at some temperature T. And we're gonna put some little hole. And we're gonna let some of the light comes out. So the light comes out. So this would be escaping light. And what we're going to do, we're going to make a graph here. Going to plot the frequency here, omega. You can also do the same thing with the lepton, with the wavelength. And we're going to look at basically the amount of energy per unit frequency. Like this. And this is what I mean by this. So when you do this, you're going to get a graph that looks like, it's going to be a graph that looks like what this means here is if I take this, and we're going to call this line here, I'm going to call this U omega. So if I look at this little wedge here, this is omega. This is so value for U omega here. And I'm going to say the width here of this little amount here is d omega. If I look at the U omega, d omega, this is going to be the energy in that light from omega to omega plus d omega. This is omega. This is omega plus. This is the energy between omega and omega plus 2. And no one can figure out how to get this curve. When you did classical physics, you could either get this part of the curve, or you could get that part of the curve. No one can get the entire curve. And so that's the whole point of what we're going to be doing. So classical physics did not give it. They either gave you this part, or it gave you that part. It did not give you the whole curve. And then Planck realized that if he came and made this assumption where he could get this entire curve. And what I want to do is show you how this works. Now, what exactly is inside here? So when you heat up this metal container, what's going to happen to the metal walls? Yeah, but the atoms are going to be vibrating. So I'm going to draw a whole bunch of here are little atoms here, and I'm going to say the atoms are all connected to each other by springs. Obviously, it's far more complicated. I'm saying the metal is basically, I can view this as being atoms connected to each other by springs. And what's going to happen? Well, the atoms are going to vibrate. And what's going to happen? Well, these atoms here are going to go from a higher state to a lower state. And in the process, they're going to give off light. So what's going to happen is that when these vibrate here, are going to give off light. And this light's going to go here. And then get absorbed over here. And then what's going to happen? Well, this one's going to do the same thing, and this is going to get absorbed over here. This one will emit absorbed over here, and so on and so forth. So I'm going to get all these photons here of different frequencies being basically emitted and absorbed on the other side of the container. So what I'm going to really end up with here is I'm going to end up with a photon gas. Gas. And what we want to ask is, what is the energy of this photon gas? What's the energy? And when we do that, we're gonna get this graph. How long have they been mowing that yard?
Rapidly growing.
So we're gonna do this. So the photons and cavity form spanning. And so what I'm going to do is I'm going to give you a derivation that's incorrect, but it's going to give the correct answer. Turns out the actual formal derivation is actually ridiculously sophisticated. When you take the second semester of advanced CNM, you do the calculation. Turns out it's really, really hard because of the boundary conditions, but there's a very simple way to get it. So let's figure this out. So let's ask what are the frequencies of the standing waves? Okay, so I'm going to just take, let's just take a string in one dimension, and imagine I have it fastened between two walls. So here's a wall here. Here's a wall here. Here's a string. This is like here. What would be the largest wavelength standing wave I could have? Yeah. Now, what would it look like? Again, a standing wave is not going to be a wave that appears to be moving this way. It doesn't appear to be moving this way. It just appears to be standing and it just has its own way. So what would happen here is I could have that string could go up a little bit like this, go up a little higher like this, and then sort of down this way, this way, and this way like that. So it's just gonna be kind of something that kind of builds. Should watch it. So, what's this wavelength? Everyone agree? Because that is how much of a wavelength? That's half a wavelength. So this is L equals 1 times half a wavelength. Okay. Let's draw another one. What would be the next one I could have?
Well, what's with the one?
Well,
Instead of just like,
this one here is going to be the number of half wavelengths. Right, because a wavelength is this. Right, that's lambda. But we only have half. Okay, so I have the same thing. Okay, what's my next highest wavelength I could have?
go,
Yeah, then what would it be? Be the way we would do this. We go up a little bit here, then down, that, up higher, get a little more, then start coming down the other way. This, flat momentarily, this, that. Okay. So now if I set this length here, how many half wavelengths do I have here? 2. 1, 2. So I can say this is really 2 times half a wavelength. I think I see a pattern. Okay, let's do one more, then we're going to generalize. What would be the next highest one I could have? 3. Yeah, I could have keep it like this, up more, back down, like this. In a case like this length here L is what? It's going to be 3 times half a wavelength. In general, what do we have?
L divided by 10. Times 2.
Okay, so in general, we have L equal to N, where N is going to be the number of half wavelengths, lambda over 2. So my lambda is really 2L over. Well, what do I know about the velocity of the waves? Well, any velocity of a wave is this is just waves on the string. How's it related to the wavelength? Frequency? Back to the beginning of the semester. What did it? Did F lambda did we not? G was F lambda? Okay, prove that.
Yeah.
Okay, first of all, I have to say, give me the proof. Give me the proof. I can go back to because you're both in optics. So that'd be fair. And no one else gets.
You start at C for them.
No. This is just nothing but. If there's no acceleration, what can you say about distance? Distance equals velocity times time. Right? So I can say distance equals velocity times time. I can have a little wave here. I have a little wave. And this wave has some wavelength to your left. And I'm going to say the time, let's look at the time it takes this wave to move one wavelength. And what will I call the time it takes that wave to move one wavelength? Period. So the time it takes a wave to move one lambda is the period capital T. Okay, so now let's do this. What distance did my wave move? What distance did my wave move? Lambda. Wave has a velocity v. How long did it take to move? T. My v is lambda over the period, or I can write this as lambda 1 over the period. And 1 over the period is the definition of frequency. This is your v. Okay, so that's where that came from. So let's put this all in. V equals F lambda, but my lambda is my buddy here, 2L over N. So my F is V N over 2 lambda. Now, how can I write this in terms of omega? I have to multiply both sides by 2 pi. If I multiply by 2 pi, this is my omega. So my omega is V N pi L. From where it's on a string. Like guitar, violin, anything with a string. Okay. Now, that's in 1 dimension. What happens if I go to 3 dimensions? I'm just going to state. If you extend this to 3 dimensions, get the exact same thing. But this N, hey, this N is going to become, this one looks familiar, the square root of n x squared, where n x is an integer, plus then y squared, and y is an integer, plus then z, when z is an integer. Yeah, we're calling that. Now, we're going to do this the following. We're going to say this equation here is going to apply to light as well. And I'm just clapping my hands and saying, thus it is. Okay. So what would be the only change that if this equation applies to light, what is the only change that we have to make to this equation? B to C. B to C. So it can be shown. Again, I hated that as a student, but now that I'm a professor running out of time for a class, I realize this thing, the other drawings of that phrase. Okay. It can be shown that this equation for the frequency of standing waves also applies to standing to light, to the standing waves of light in a cubical cavity. Like cubical. Yeah.
So we don't have to do ugly correct volume scenarios.
And plus, we know what happens when a cube gets really big.
Seems like it's very, very big.
It becomes a sphere.
Is that a problem? Because L changes depending where you look around the cube.
What happens is if you didn't, let's say you, let's say you had a spherical, you had a rectangular solid. In other words, the x length is A, the y width is B, then the z width is C. What happens is that instead of getting this, you get this V, you get this pi, and then what you end up with is then half power of nx over A squared and y of B squared z. And then what you do is you then set the A or B or C or L. If you don't assume something, rectangular, always bad. You can still do the sphere one. You can do the cylindrical one, but if you have like some arbitrary cavity.
I think the point of the cavity just to hold on to the electrons to keep them.
Well, you're basically you want basically the photon gas. And you want it to just come out. And what we're going to do is we're going to say this is going to be a good model for a star. It turns out it's a really good model for a star.
Big stars.
So what we have here is that for light. We have the exact same thing. We have the C. That's the only difference is we put in the speed of light N I over L. So you tell me how we'll set up the equation, then we'll solve it tomorrow. So I would have, so the energy of a photon gas is, I'll call this U. And I'm going to take the energy of one photon, which is what? H omega. Now, photons are a boson. And they have this energy H omega, H bar omega. How many photons would I then have with that energy? That would have to be given by the Bose-Einstein distribution. So I'm going to have my Bose-Einstein distribution here, 1 over E, the H bar omega over kBt. Because the mu for a photon is 0, minus 1. Now we need another factor here. Yes. What do you think that factor might correspond to? How many states have an omega? There's a certain number.
It has been.
Yeah, so maybe what we might want to do is make a graph here of NZ and make a graph here of NY and make a graph here of NX. And there's no restriction on this N value. So I might be out here to some really, really large N value. Hey, what is this starting to smell like?
Onions.
Yes, okay. I can actually look at some shell like this and give it some little width to it like that. And all those will have the exact same end value. Okay, this is exactly what we had when we did the electron theory of metals. What's the volume of the sky? Okay, there's a 4 pi n squared dn. And what does that represent? 4 pi n squared is, well, this is the surface area of the sphere radius. The dn then gives me what? The thickness. So this whole thing would be the volume of a whole onion layer. How much of the onion layer do we have? 8. Only an 8, because again, our ends can only be positive. So I divide this by 8. And for some magical reason, I have to multiply by 2. What else do you know about light? Again, you two should know. Actually, I think everyone here should, because I said in another spectroscopy class, I know that to be true. This is just conventional spectroscopy. What do you know about light?
Pretty strong.
It's polarized. It can be polarized this way. It could be polarized this way. So this right here is the number of polarization states. Now, what would I have to do? I would then have to integrate over all possible values of n or omega. So I can have an integral here going from 0, and there is no restriction on what the n value can be. It can be anything. This has to go off to infinity. And what we're going to do, we'll tinker with that tomorrow. And then when we do that, we are going to get that curve. Okay. Now, if you look at how those derivations are usually done in modern physics, they don't do any of this. The equation just comes out of nowhere. And that just drove me nuts as a student. When I saw something, I can accept some things saying it can be shown. But at some point when there's just this utterly random equation, that's yes, okay. So we do that, and then we're going to figure out what the temperature of the universe is. What's the temperature of the universe? 2.73 degrees. I'll show you how we can actually know that for a fact. It's not an accident that it is there. And that's going to actually be evidence for the Big Bang. Wait, have a good day. Kelvin. Well, degrees Kelvin. Kelvin.
Thanks.
So if any of you, want to submit